So, if we had a pulse travelling and a pulse travelling, this is what we set up yesterday when Hal sent a pulse towards me and I sent a pulse towards Hal. Let's suppose that that represents T1. Obviously, a certain time period later, they're going to be getting closer together. This might represent T2. That's an arrow. And then for the third one, when they meet, their amplitudes actually superimpose. Okay? Now, it's a bit tricky to watch it in real time, but when those two pulses meet, you've basically got an amplitude and an amplitude. They superimpose, and you get a larger amplitude. Okay? Now, we've run out of room now, but obviously what we saw yesterday is that those two pulses will just continue on travelling past each other with their initial energy. There was no loss in energy. Okay? There was no change to the shape of the pulse. Now, what we will suggest is that this would be known as constructive. Oh, look how crap my handwriting is while we're screen recording. Constructive oh man, this is just very bad. Constructive interference. So they're working together, their amplitudes are in the same, they're both positive, and so a positive and a positive makes a positive. Okay? Constructive interference, and I'm missing my blue T3, which is greater than. You get the idea. We're trying to show a couple of snapshots in time. Now, there are, oh look. Oh, look at that. Yeah, cool. Here's an even better diagram showing 5 different time periods. Here's our 2 pulses. Now, these guys work together constructively. Brownie, could you shut the door, please, to keep the sound out? Rather than me wasting the second line, let's look at this one. You've got 2 pulses travelling towards each other, but now one's positive and one's negative. Okay? We did this at the very end of yesterday's lesson. We said, right, I'm going to make a pulse on the other side of the slinky, send it towards each other. Again, this is happening really fast. The pulses were travelling really, really quickly. For a brief instant in time, if you sum the amplitudes, a positive with a negative, it cancels out. But again, this is just a brief instant in time. The pulses don't disappear. They suddenly reappear and travel through each other. Again, unaffected. All right? Yeah, positive pulse continues on the positive side. We would call this the opposite of constructive. Say it, someone. Destructive interference. Where they cancel each other out. You have a positive cancelling out with a negative to give 0. Okay? Whereas over here, you had a positive and a positive producing a much larger amplitude. So the sum of the 2 waves can either work together or they can cancel each other out. They can either be constructive or destructive, both relying on the superposition of waves. And just for funsies, you can send some weird shapes, all right? And at any point in time, you're simply going to go, what's my amplitude? What's the amplitude? Add them together, okay? So again, you can sort of see we've superimposed this guy on this guy for a brief snippet in time. Yes?
Is destructive interference about noise cancellation?
Did you sneak into my YouTube channel and watch last year's lesson? Because that is exactly how they operate. Give me 1 minute and we'll fill out the second line on the top of your page. Gentlemen, this is not how it happens, but what you've just done is you've put a wave on a wave, and this is a simple analogy as to how you can send information through radio waves. You can put a sound wave on a radio wave and broadcast it out. So literally your voice, you can take your radio wave and you can modulate the frequency So my sound, my voice is just an alternating pressure wave. I can convert that into a electromagnetic signal in the frequency. So, look, it gets a little bit tricky, but I could take my sound. Here's me just blabbling out stuff. That's my voice. Okay, I could place that onto an electromagnetic wave. How good am I drawing? Oh, close enough. All right, so you could chuck that onto my electromagnetic wave, and off it travels at the speed of light, really, really fast, and someone out there can have an aerial, and that jiggling of frequency modulation will make the electrons jiggle, and then you can convert it into sound. That's called frequency modulation, FM. There's one other way to do it. You can do amplitude modulation, which is where you can vary the amplitude, which is known as AM. So there's two ways that you can send stuff on an electromagnetic wave. AM would change the amplitude of our electromagnetic wave, and that might look a little bit trickier on my diagram. That might be doing stuff like this, where we change not the frequency, but the amplitude. I'm just, anyway, this is a very bad diagram, but
How did the first diagram show the change in frequency?
it didn't, so don't worry about it. Let's go back to, was it Harry that asked about the noise cancelling headphones? On this next line, this is some really cool technology. And obviously they're quite expensive headphones. If you have your headphones and you want to listen to your podcasts, and you put it on and you want to hear only what's coming out of the speakers. But right now, there's some noisy bloody tractor outside beeping and pushing dirt around. And those pressure waves are coming through the headphones, and they're pushing my eardrums as well. And I'm having a bit of difficulty trying to listen to my podcast because I can hear this beeping and engine noise. Let's take the outside noise and suggest that this is what its pressure wave looks like. There's a beep. Draw this. There's the beep of my tractor. Alright? And this pressure wave is travelling through the headphones at the speed of sound, really, really fast, and travelling into my eardrums. So it's happening really, really quickly. What your noise cancelling headphones can do is they'll have a little microphone in them, and they're listening for any outside noise. And I use the word noise instead of sound. The stuff, the junk that we don't want. Listen for the noise and capture it really quickly. Interpret it and process it and spit out a wave into the headphones that destructively interferes with it. So it's going to try and, at a really quick time, send out a wave that when we combine them destructively, it cancels out. So I'm going to try my best to draw. I can't. I've tried it many times. It doesn't work.
Really?
Yeah. I like what you're thinking, but so try your best, and obviously the crazier your graph, the more difficult it's going to be, but try your darndest to draw there. Alright, well, that doesn't look too bad. So this could be outside noise. And so it's got to happen really, really quickly. And the speaker that's inside has to send out this signal at the same time. It's almost cancelling out the pressure wave. So it's taking the pressure wave and it's just kind of cancelling it out so that no pressure wave of the noise reaches your ears other than your audio, your sound, your music, your podcast, whatever it is that you want to hear. It's not perfect, but it can work. So if you've ever been on a long flight and you place your head-cancelling headphones on, you can't hear the engine, you can't hear the noise in the cabin. Okay? It's not perfect, but it can remove a lot of that noise. Yes?
You could probably work out like the delay you needed if you knew the velocity through the headphone material, right, and the thickness of the material.
Yep. and again, it would literally be the distance between your microphone listening and the speaker that's cancelling. The speed it takes for that pressure wave to travel from that point to that point, that's the time that your processor has to interpret the noise and then produce the cancelling. So if it's offset, then it's distance versus time. So, but as we know, computers can work a hell of a lot quicker than us humans. Oh look, here we go. This is a better way. This looks like frequency modulation. So this is a better diagram of how you could take someone's sound, convert it into an EM wave, and throw it on to another EM wave. So this is a wave upon a wave. You take this and beam that out across the land, and on this wave could be 99.3 FM, which might be triple J. Okay? And so when you tune your radio to 99.3 megahertz, it takes this and chops it into a 99.3 megahertz wave and outspits that. And that is then turned into a electrical signal that travels to your speakers. Okay, so that's probably a little bit better diagram of how we can put waves on waves. It's not just sound, it's also water, it's electromagnetic radiation, all of, these all act as waves, so you can do this cool stuff. Okay? This is a very bad diagram. However, I just want you to quickly analyze this at a few different points. You'll notice that these two waves, it's one wavelength, but you might notice that this wavelength below has been shifted by half a wavelength. That's important. If we can shift it so that it is out of phase, and we've spoken about wave motion being out of phase by half a wavelength, it will perfectly cancel. So I might just put a little note here. Shifted? That's an S. Shifted. Okay? And so just below that, gentlemen, could we please draw a very simple flat line? Zero amplitude. Okay? That would be a perfect example of destructive interference due to superposition of waves. Putting one wave on top of another. Here they are in phase, so again, they're going to work together. You've got a trough meeting a trough, you've got a crest meeting a crest, your amplitudes will superimpose, and you're just going to draw a much larger amplitude. Okay? If you can draw a little bit better than me. Okay? And again, if we had a scale on our y-axis, you simply take your maximum values, add them together, and that becomes the maximum point of your superposition. Where's your booklet? Oh, I was going to print you off one and never did. Hang on. Maybe. I don't think it's in this second booklet. There's a couple of brief hashes. Oh, man. You're the luckiest kid. This is the next booklet, but it's overlapped. Still, not letting you go to get a drink because now you've got some writing to do. Toilet. Are you drinking out of the toilet? You asked to go to the toilet. Can I say no? Go quietly, return quietly. This next one, gents, is a little bit trickier. Because now, boys, can we just have us back on task, please? Now, our waves they're not half a wavelength, they're not one wavelength, and in fact they might be a completely different shape. They're out of phase by not a nice value. It's not a half integer, not a whole integer. And if you're ever getting something like this, you simply have to analyze it at different points. So let's analyze it at x equals 0. Well, we've got a negative value and 0. That would give a negative value. So I'm just going to draw a dot down there. It is a bit low. Then, let's analyze at this 0 point. If we track upwards, we're up to about there, so I'm going to draw it about here. And then at this maximum, we're still going up, so I reckon it's going to get even higher still. Now this one's dropping, but this one's rising. So I think from about here, I reckon if you've got that and that, I think it's increasing at the same rate as the other one's decreasing. So I reckon for this point, it's probably going to flatline for a bit. Then they're both dropping. So if we get to the turning point here, then I reckon we're going to be down a bit. Then we can analyze a turning point here. We're at 0 and a turning point. So I reckon we're below the x-axis down here. And then maybe turning point, analyze where it's at, 0. So we're still maybe something like this. It's not the best method. Obviously, the more positions that you analyze, the more dots that you're going to have. Okay? So it depends how long you want to spend. We did 1, 2, 3, 4, 5, 6. We're going to have 1, 2, 3, 4, 5, 6 dots. Try and just join the dots.
I reckon between those two dots
It dips a little bit? Possibly.
That's my guess.
Well, let's have a look. We've got that's rising, that's falling. I know. I reckon that one's rising while that one's falling.
Or not? I think between like.
I reckon it's probably. I reckon it's going to probably do that. But anyway.
Alright, but like the first two dots.
The first two dots.
Sorry, the two dots which are even, the two peaks. Yeah, I reckon between those two it dips.
Down?
Yeah.
You're joking. You think it does something like this?
Yeah.
Outrageous.
Oh, if you think about it, right?
I don't want to think. What?
Oh, well, as you approach a peak, right, the rate at which you're changing decreases.
No.
So as it's leaving the peak, it's probably like decreased a lot, while it has only got a bit more to increase.
From here, that's going up while that's going down.
Yeah, but that, like
You reckon that's decreasing at a greater rate than that's increasing?
yeah, at the middle, yeah.
Alright. Okay, you draw it how you want.
Or
It could be.
It's definitely not flat. Yeah.
Alright.
Marcus is right.
Marcus is right.
It could be the other way.
Marcus is right. Okay.
I don't